Chapter 2.1, page 102, we're going to talk about vectors. A vector is something that is different from a regular number in that a vector is something that has not just how much it is, but it also has a direction to it. For example, an average number, you might call it, I don't know, 5, right? That's a number. A vector is not just 5. It's 5 with a direction on it, like this. Okay, the arrow here means direction. Now, what direction is that? Well, it'll be given to you. For example, it might be like that. And the length of the vector is measuring how long it is. So the 5 means this is 5 units. That's how long it is. That's called the magnitude, and is sometimes written with the absolute value. So the absolute value of a vector is how long it is. And then, but the direction is special to the vector, whatever it might be. Okay, it might point, I don't know, east, up, something. Anyway, so that is a vector. And then two vectors are the same if they have the same magnitude and direction. All right, so let's turn to the next page. And then there is, what is that? The vector has some beginning point, ending point. Yeah, we're not that interested in it. And all right, so that's so example 2.1. Please draw a vector. How would you draw it? Like for example, you might have a vector that starts at point 1,1 on the plane, and then it ends at point 8,5, like you see in the book. And that will be a vector. See, it starts there and end there. That's called a vector, and it has a certain length, but and you can calculate the length by the Pythagoras theorem, but we'll skip that for now. We'll do that in a little bit. So let's move on to the following page. Now, the vector sometimes can be multiplied by some number that isn't a vector. That is just a regular number. It's called a scalar. A scalar just means a regular number, and the scalar multiplication just means, for example, if you multiply the vector 5 by say 2, okay, then it becomes 10, and that is now it's twice as long, but it points in the same direction, and that's how you multiply scalar numbers. Of course, that's multiplying by 2. If you multiply by half, then it's only half as long. That's the one that got multiplied by half. And then if you can even multiply it by negative numbers, say minus half. What happens when you multiply it by minus half? Then the vector is the same length, it's still half, but it goes in the opposite direction, not just different, but exactly opposite. That's how you multiply by a negative number, a negative scalar. Again, a scalar is just a number that isn't a vector. Okay, so that's that. Now, next thing we're going to talk about is how to add two vectors together. To add two, say let's have two vectors, okay, like this, and the other one maybe goes something like this. And how do we add these two things up? You imagine the vector to be some kind of like a force. One way to add it is you line them up end to top, or something like that. So here's the one, okay, and then you draw this one right at the tip of the other one in the same way. That looks longer, doesn't it? I mean, it's the same length. And pretend it's the same length. Anyway, just put this thing at the end of tip end of the other one, and then you draw the third vector that's from the beginning to the end of the very end. Okay, that's adding. So this is vector 1, let's say, and that's vector 2, and then v3 is by lining stuff up like this, and v3 equals to v1 plus v2. That's one way to do it. Another way is you line up both vectors. This is v1, okay, and then this is v2. You line up both vectors. I'm drawing it not tilted. Pretend it's tilting the same way. I think this looks too vertical. It should be tilted. But okay, pretend it's tilted just like that. Okay, and here's v1 and v2, and then what you're gonna do is draw a parallelogram from geometry. So you draw a parallelogram and draw this thing all the way to the end of the diagonal of your parallelogram that is based on these two vectors. Now, if you do that, then this is exactly the same as that. Okay, you're just drawing it slightly differently. This is called the triangle method. This is called parallelogram method. They're the same thing, but that's how you add two vectors together. Now that matters because what happens is that in real life, for example, you have, say, here's you. Okay, you're standing here. I'm looking down from the sky at you. So this is you, and then there's a rope here, and somebody's pulling you this direction with a rope. Somebody else, that's V1, okay? And then somebody else might be pulling you this way with in a different force. All right, so this guy is pulling in this direction with a certain amount of force, and that guy is pulling in this direction. In physics, they teach that if that's the case, then the resulting force, okay, it ends up being the same as if you add the two vectors together. And this is V3, where V3 equals to V1 plus V2. So if two guys pull you like this, it's the same as if they pull you this way with the two forces added in a certain way. But the addition isn't just direct addition. The addition is added with, that is, you need to calculate this third triangle to figure out exactly how long it is to know what the force is. All right, so anyway, let's move on. And what's this? What are we doing? Okay, so turn the page. Yeah, we're adding this stuff together. And there is one point I should mention is the third, is that when the V1 plus V2 is going to be less than equal, V1 plus V2, the magnitude of this thing, okay, is going to be, which is equal to V3. Okay, V1 plus V2 is just V3. Now V3 is going to be less than or equal to each one of these things, V1 and V2. The reason for that is this is called the triangular inequality. This comes from Euclidean geometry that states if you have here's my A, okay, here's B. In Euclidean geometry, there's an axiom that states that the shortest distance between 2 points A and B is the straight line. So therefore, this line is always going to be less than any other way of getting there. Okay, this is not the straight line, therefore it's longer. And that's where this inequality comes from. All right, now, having said that, let's look at example 2.2. You're supposed to sketch some vectors. Let's see, all right. So please do example 2.2 as part of your homework. Now in this video course, I will assign various homework, sometimes from the examples, and always from the problems basically, and sometimes even from part of the book that isn't even the example, is just talking about something. And when I do, I strongly recommend that you do all the homeworks that I assign. The homework assigned will all be in the description of the video, but I will also mention it in the video itself. The important part is doing all these homework is extremely important in understanding the course material. Now, I'm a mathematician, but I'm also an efficiency expert. So I have designed this class so that you can, in such a way that you can get everything done the fastest and easiest, both, if you do the homework that I tell you to do. Each homework, I choose them very carefully. They're not just random numbers I toss down, okay, just for the fun of it. It doesn't, so everything is designed so that you have a great time of doing Calculus 3 and truly can learn it as a hobby. So please do the homework. And the first one I want you to do is example 2.2, and as part of your homework. I will write it down. Now, there is one exception to what I just said, is what if you already had Calculus 3 years ago and you're just doing this as a quick review? Now, in that case, you don't have to do all the homework, but I recommend that you do all the homework that I put a star on it. If I put a star on it, you better, you should do it, because that will give you a strong, proper review. So anyway, so that's example 2.2, and let's flip over to the next thing. What's this? Okay, example 2.3, which is the vectors. The vectors can be drawn in a coordinate system. as we have seen earlier. Okay, for example, in this example, what am I doing? 2.3, which is on page 108, we have, say, two vectors. You can draw them, well, from point A to point, from some coordinate point. See, like the vectors start at one point, some point, and end somewhere else. And that's about all. Okay, please do this example as part of your homework. So next, let's flip to page 109, where we look at the vector in something called the component form. So if you have a vector, what you're going to do is that you're going to move it to the origin and move its base to the origin. Okay, here's the origin, and you draw your vector some way, and then here's how long your vector is. And the vector, of course, at the origin, it has from origin to wherever it's supposed to be, it has a coordinate that's called xy. So we will call the vector that goes from the origin to xy, v equals to brackets. What is that called? Who cares? Yeah, x comma y. As of right now, YouTube does not allow me to type the larger than or bigger than or less than symbol into the description. I don't know why. So so I'll figure out how to handle that later. But anyway, the point is, so that is a vector. So you move your force arrow, okay, to the origin, and that's called a component form. Component forms, which means that if you have some vector that's in the middle of nowhere, right? It starts here and ends there, then you can move it to the original point by simply subtracting the various coordinates. Then it will be, yeah, for example, the rule says if you have some vector which is, what is that, from xi I yi to xt yt, then you just subtract each one properly, and that's your new vector. That's the rule. And so please do example 2.4 as part of your homework to see how that rule goes. All right, so next, the following page. Now, once we have defined the vector this way, what is its magnitude of this thing? That is, how long is it? Well, how long is it? As you look at it, and you know exactly how long it is. You use something called the Pythagoras theorem, okay? A beloved formula since childhood. So we'll use the Pythagoras theorem, which is this x squared times plus y squared, and then take the square root, and that is the magnitude, that is the length of your vector. Now, if the vector doesn't start at origin, then you have to do some subtraction. But in this case, it does. Nah, let's not even worry about that. The point is x squared plus y squared. Then take the square root. It will be equal to. I shouldn't be squared here. Let me erase. Yeah, this is just x, right? The formula, however, says you need to do the x squared y squared. Anyway. So let's go to the next page. Now, another thing I should mention that is that if the vector is 0, then its magnitude has to be 0. Otherwise, it doesn't make any sense. Yeah, you cannot have a vector that has some magnitude, but somehow it's not 0, okay? Yeah. Anyway, let's move on. What is that? To the following page. We are going to do something like various operations of the vector. Now, to do multiplication, to multiply a vector like this by some number, say 2, you will multiply each component by 2. That is, and so you have 2 times v, that's 2x and 2y, etc. That's how you do the scalar multiplication. If you do vector addition, if you add two vectors together, you just add x with the x coordinate and y with y coordinate. See, like your book shows, piece of cake. See, this is yeah. You just do basic addition and your vectors all added. So please do example 2.5 as part of your homework. Next, let's go to page 102, where we have a bunch of theorems. Okay. That is vector addition and subtraction and multiplying by a scalar, which is just a number, not a vector, all works like basic math. Okay. Now I'm not going to go over that And in fact, your book even gave all the names, what these things are called. What they are called is not that exciting. The point is, this is how it works, and it's been working since grade school. So that's how, quite easy. Now at this point, you're probably thinking, wow, oh, this is so easy. Is it always going to be this easy? No, well, it's not. It won't be easy long. Anyway, but well, now it's easy, so let's enjoy it. Or put up with it, because easy just means grunt work, right? You're stuck with doing addition again. Ugh. Anyway, but either way, let's we'll apply self-discipline and do some grunt work like thing, because as in all hobbies, we're studying math as a hobby, but as all hobbies, some grunt work is required. So having said that, please, yeah. And then of course the vectors, if you look at it from a trigonometric point of view, then you have this. Okay, say you have a vector, this is on the next page or something, then if the vector makes some angle with the x-axis, therefore the x component is v cosine theta, absolute value, and the y component is v sine theta, with v in absolute value. And that is just, yeah, that basically comes without saying. Your book actually proved all this, proved the commutative property, etc. Let's skip it. It's too obvious, okay? And we are in Calculus 3, and we're not going to prove commutative property. Are you kidding? So let's just do example 2.6. Next, let's go to page 114, where we are looking at unit vectors. The unit vector is a vector that has the length of 1. So if you have a vector that has length that isn't 1, then you divide it by its magnitude. You know, if your vector is 5 and pointing some direction, you just divide it by 5. So now it's a unit vector. So it's 1 because the length got shrunk down to 1, but it's still pointing to the same direction. And that would be your unit vector. So please, and that division has a name to it. It's called the normalization. Why do we need a name for that? That does happen a lot. So that's why there's a name for it that I haven't forgotten even. So that's how important the name is. I've forgotten what commutative, associative, whatever tif. No, who doesn't know that anyway? So, but normalization actually is I even remember what it is, so it must be useful. So to shrink down some vector into to be length of 1 is called normalization, and you do it by dividing the magnitude. That is, how long is it? Divide it, and then you got 1. So so please do example 2.7 as part of your homework. Next, let's go to the next page, 115, where we're going to talk about something called the standard unit vector. What does that mean? A standard unit vector is we have something called I, okay? I is equal to 1, 0. And then something else, this is a vector, okay? I is a vector. It goes from the origin to 1, 0. So I goes this way, right? Yeah. And anyway, J is the other one along the y-axis, which is 0, 1. So J equals to, okay, J equals to 0, 1, which means J, did I draw as parentheses? I mean the brackets, okay? These are vectors. So I should draw it as a bracket, or whatever this thing is called. I don't even think it's a bracket. Anyway, let's draw that thing. And so these are the vectors. Now, if they are vectors, then we can use these two basic vectors to represent all the other vectors. For example, if you have some standard vector x, y, okay, and that can be written as x times I, come on, I, okay, x times I plus y times j. And if you look at it for a few seconds, you can see why. You know, because these are is the same as going this way and then going that way, and that's the result. Okay, and so now that is v, and so that's yet another way of representing the vector, is that you can represent it in terms of I and j. Did I write I here? I mean j. Now remember, this I has nothing to do with the imaginary number. Okay, this I is a vector that's defined as 1, 0. That is a vector that's 1 unit long that goes this way, one distance. And j is very similar to I, except that it goes up. All right, so that's yet another way of representing any vector if you feel like doing that. So please do example 2.8 as part of your homework. Next, let's look at example 2.9, which is on page 117. We are going to apply some force. Okay, one force goes this direction, and then the other force goes a different direction. And what is the resulting force? Well, the resulting force, as we have seen earlier, you just add the two vectors together. That is a fact that's taught in physics, but right now, let's just assume that's true. Okay, and so you add it together by doing the parallelogram. And in fact, you're not even going to do that. You're just going to add the components together. That is, you're going to break each vector down into its component parts, x and y, add up the x's and y's, and then that's your resulting vector. So please do example 2.9 and also 2.10, the exact same thing. The airplane is flying this way, the wind blowing a somewhat different way. You need to add the vectors together and you got the result. So please do both of those problems as examples as part of your homework, 2.9 and 2.10. We have come to the end of the section. So for homework for this section, please do problem on page 119. Please do problems 5, 7, 9, 13, 17, 21, 27, 31, 35, 43, and 51. That's not that many problems, and they're all very, very short. They're kind of like, this. You do some quick addition, which sounds boring, and it kind of is, but we're just starting out this course easy. It's not going to be boring or easy for very long. So please do your homework, but I'm not going to go over them because they're all very short and short addition like thing with a little bit of a Pythagoras theorem thrown in. And so please do that, and I won't be going over homework for this section, but I will go over it in the future as things get a lot rougher than this.